Hey, welcome again to Humke Study. Today I'd like to talk about the first section of the next chapter, which is on subspaces. And so to understand this subspaces thing, I'd like to first of all talk about what do we mean when we talk about the spaces. So the full spaces for us consist of the real line, just numbers, R2, all ordered pairs, A and B are free, R3, which consists of ordered triples. And these squiggly brackets put a bag around these. So again, A, B, C are free. So these are considered the spaces, kind of like the universe that you live in. And a subspace is part of one of these. And so as an example of what we're talking about, for example, a 2D subspace, two-dimensional subspace of three-dimensional space. So what are we talking about here? Well, first of all, this tells you where the thing is going to lie. So this is going to be part of three-dimensional space. And 2D subspace has two parts, subspace and 2D. The first thing, subspace, will mean the arithmetic is just like the arithmetic of any of these, but in particular like R2, meaning three things. 0 is, let's call S the subspace. 0 is in S. Written 0 is an element of S. One of the things in S has to be the 0 vector. So for us, the 0 vector is in R3. So this is meaning that the ordered triple 0, 0, 0 is in S. Secondly, if U and V are two vectors in S, then U plus V is also in S. And thirdly, if you take any real number T, so this is any real number, so this is can be any number, then, and say some vector is in S, then T times U is also in S. So these two together say all linear combinations of S are also in S. If you take stuff from S and you do linear combinations, it remains in S. I'm going to talk about this 2D part. So this is what subspace means. But I think it's good to think about this 2D part also at the same time. S is 2D means there are two linearly independent vectors U and V, say, so that S equals the span of these two. So two-dimensional has to do with the fact that there are exactly two linearly independent vectors, so that S is the span of those two. So the 2 in the 2D has to do with the, by the way, new flaming pink. The 2 in the 2D has to do with the fact that there are 2 of these vectors and S is the span of them. And since S is a span here, it automatically contains all of these properties. So S being a span of something tells you immediately that S is a subspace. Subspaces are the things that are spans of other things. And if it's 2-dimensional, then it's a span of 2 linearly independent objects. If it's the 3D, it'll be the span of 3 linearly independent objects, and so on. So it's nice to think of these together. But this is the definition of subspace down here. And actually, this is the definition of 2D. Now, all of these vectors that we're talking about here are 3-dimensional vectors because we're talking about a subspace of R3. So all of the vectors are 3-dimensional. If this would be a 4, then all of them would be 4-dimensional vectors, but all the definitions are the same. It's just that the notation changes depending on what the home base is, what the home space is. So this is the basics of it. The definition, 2 parts. And I thought we could look at some examples. So let's look at some subspaces of R2. Various subspaces of R2. Every subspace can be written as a span. So let's start off with just writing something as a span. So we'll start with span. And this will be our first subspace. So I'll call this S1, the first subspace. And I need to know what this is the span of. What this is the span of. Snow, do you have something? Sure, like 1, 1, 1. Well, no, not exactly, Snow, because 1, 1, 1, it's a fine vector, but it's not in R2. There's R2 up there. Oh, okay, just 1, 1 then. Yep, just 1, 1 is just fine. So if you look at the span of just 1, 1, that is a subspace. This is sort of an easy one. It means all linear combinations. Well, you can only take multiples. So this is all the vectors of the form A, or let's call it SS, such that S is free. Can be any real number. And if we graph that, that's just the line where the Y value equals the X value. Brilliant blue, also new. And so this is the picture of that subspace. Notice that it contains the origin. That's a good thing to check anytime you're given a collection of things to see if it's a subspace. Make sure it contains the origin. And then it has to contain all linear combinations of stuff that's in it. And in this case, it just means all multiples of 1, 1, 1. So this is a subspace. If Snow would have given me a different vector like 1, 2. So here is the vector 1, 2. And if we take all linear combinations, that would mean all multiples. Another line containing the origin. So S2, the span of 1, 2, means all things of the form S2S, such that S is free. This is also a subspace. So every line through the origin in R2 is going to be a subspace, and it will be 1D because each one of these is 1D because this is each one of these is linearly independent. So these are 1D subspaces. 1D things are one-dimensional. And what about can you do anything else? Can you get anything other than a line in the plane here? we're looking at subspaces of R2. Can you get anything else? Ohm, what do you think? Yep. Well, what would it be? 0. 0. Oh, I think I see what you mean, Ohm. You mean if you start just like Snow did here, but you don't use 1, 1, you use the 0 vector. Yep. The span of the 0 vector, it doesn't get you anything. You add it to itself, you take multiples, you only get 0. So the only thing that you get with the span is just 0. Yeah, that is, that single point, 0, is a subspace. And this actually would be 0-dimensional. There are no, 0 is considered linearly dependent even by itself. So there are no linearly independent vectors that span this. So this is 0D, kind of the easy one. There's another one too. And I'll just do this. If we take, this would be the 4th one we did. If you take the span of, say, 1, 0, and 0, 1, you get everything. You get all of R2. Every vector in R2 is a linear combination of these two. But if you would take another linearly independent set of 2 vectors, like 1, 2, and 0, 1, the span of these two is, again, you can get everything, because from the unifying theorem, if these are linearly independent and you're in R2, the span is R2. So there are only 3 categories of subspaces of R2. The origin itself, the whole plane itself, and there's only one thing in each category, but then any line containing the origin is also a subspace. And so that's the geometry of these. If we wanted to do R3, what are the subspaces of R3? What do they look like? Well, again, any subspace, I'll begin with S1 again. Any subspace is going to be the span of something. So you're allowed to put as many vectors in there as you want. If you put in linearly independent ones, then you're going to be able to tell what the D is of each one of these. But the things you're going to put in there are 3D vectors, because you're in 3 space. So let's put in some 3D vectors in here. Snow, what do you want to put in this time? 1, 1, 1. Well, that's what you said last time. I know it didn't work, but it works here. Yeah, it works here. 1, 1, 1. We could put that in. Anything else? Anything else? Okay, 1, 0, 2. All right, we'll put in 1, 0, 2. Is this random? Yes. So let's take the span of these two. Are these linearly independent? Yep, that's right, Ohm. These are linearly independent. So this is going to be 2D. This is be a 2D subspace. And the span will consist of all linear combinations of these. So let's see if we can picture that. We take 1, 1, 1. That's this vector right here. And we take the vector 1, 0, 2. That's this vector right here. So we have 2 lines, 2 vectors. In just a second, I have to erase my plane. So we begin with 2 vectors, and we can think of these as each one individually. If you take multiples, that's allowed because any linear combination, so you can take multiples of these. So this line is going to be in our span, and this line will be in our span. These two vectors with the free variables that come with the word span, S times 1, 1, 1 plus T times 1, 0, 2, S and T are free. And that's, after all, what span means. It contains those two lines. Those lines intersect at the origin. And two intersecting lines determine a plane. So what we've got here is a plane. It is the plane determined by those two lines. And that is what this subspace is. Now, this is not R2 because R2 consists of just ordered pairs. This consists of ordered triples, but in a way, these ordered triples, if you use addition and scalar multiplication and so on, if you just live in this plane, it's a lot like living in the plane, R2. Everything works the same, but these guys don't live in R2, these live in R3. So this is a subspace. S1 is a subspace of R3. It is a plane, looks just like R2, but it's not R2 or D2. Now the book gives you several methods for checking. You should look at a few of those examples for checking subspaces. The basic idea is to take what you're given and write it as a span. So if we look at this set, for example, the set of all, let's say A, B, C, and I'm going to put a property here so that A plus B minus C equals 0. So this is a collection of vectors, A, B, C, that satisfy this rule. 1, 1, 1 is not in there because 1 plus 1 is 2, minus 1 is not 0. But 1, 0, 1 is. 1, 0, 1 makes this rule true. So some vectors are in and some vectors are not. But if you incorporate A, B, if you solve this last equation for C, C equals A plus B, you can incorporate this information by subbing that value in. A and B are free variables. A, B, C are not three free variables. This equation means they're not free. Two of them are free at a time, but once you've established two, the third one is fixed. So that's not free of the other two. But now you can split this apart. You can put the A's together, A, 0, A, plus 0, BB. A and B are free. And then you can write that as all multiples of 1, 0, 1 plus multiples of 0, 1, 1. A and B are both free. So this is equal to the span, all linear combinations. These are linear combinations, add, multiply by constants, of two vectors, 1, 0, 1 and 0, 1, 1. Is S a subspace? Yes, it is. You can write it as a span. And in fact, these two vectors are linearly independent. So this is a 2D subspace. var3. So what do you need to know about this stuff? I'll ask you the definition of subspace on the next exam. It's one of the definitions. So you should know that definition. Has the three properties. 0 is in there. Add any two vectors that are in there and you get another one. Any vector in there times any scalar is in there. So that is the definition of subspace. But then on the problems, I want you to determine, is something a subspace or not? And the exercises in the book are about that. I think that's plenty for tonight. So in any case, I hope you have a good rest of the weekend, but not too good. And I will see you Monday.